Good day, everybody. Today we're going to look at electromagnetic radiations. And in particular, we're going to look at reflection of electromagnetic radiation. In our case, of course, as I've said before, this is really magnetic induction. But what we're going to do, we're going to reflect the magnetic field that is generated by the alternating current. The alternating current, just to recap for somebody that's not seen our demonstrator before, we've got a DC power supply that's supplying a DC current to a flyback oscillator. Our transmitting antenna consists of 25 turns of enameled copper wire with a center tap, another 25 turns of enameled copper wire and then the center tap, of course, forms part of the flyback oscillator. That oscillator is going to create an alternating current in what we call now our transmitting antenna. Our receiving antenna is this antenna over here. For you that have seen these videos before, you would have known that this is in fact 50 turns of enameled copper wire. You'll see that right now I've oriented the antenna in a funny position and actually attached it, if you've seen the previous videos, at such an angle that very little electromagnetic induction, or in this case magnetic induction, is actually transferred to our receiving antenna. Now, the purpose of this exercise is I'm going to show you reflection in the electromagnetic world. Electromagnetic reflection is going to reflect the magnetic induced field onto the receiving antenna. Just to recap for those that you haven't seen the lab before, I've got two oscilloscope probes here. This is the oscilloscope pre-processing unit that's going to process the waveform. For those of you that don't know what an oscilloscope is simply a device that shows the waveform in time so that we can see the actual waveform that is generated in the transmitting antenna. And through the probe on the fly leads here, we'll see what the current is that's being induced in the receiving antenna. The display is sent to the laptop over here, and you'll be able to see it on the laptop. I've got a separate camera that's taking a shot of the laptop, and that'll come up as an insert on the video. Right, so without further ado, let's switch on. Just for those of you that haven't seen the previous videos, this digital multimeter over here measures the voltage that I've got over the oscillator here. That's the DC voltage from the power supply over here. And this digital multimeter over here will measure the RMS current drawn by the oscillator from the oscilloscope. In other words, I've got in circuit this particular multimeter. This is going to measure it in milliamps. Right, so without further ado, I'm going to switch on. Those of you that have seen the previous videos, you'll see the normal waveform, the waveform that's created by the oscillator in the transmitting antenna. The polarization of the receiving antenna is in a poor position, but what I'm going to show you now is how I reflect the magnetic field, the alternating magnetic field, and how I reflect that onto the receiving antenna. And watch the LED closely as well. I'm bringing it closer, and there you can quite clearly see, you can see the LED also. I'm not touching any of the transmitting antenna or receiving antenna, but you can quite clearly see, incidentally, that's on a different scale now to make it more sensitive, but you can quite clearly see how that current is being induced. I take it away, you can see on the oscilloscope, no current reflected, or shall I rather say, no magnetic reflection reflected onto the antenna. Watch closely as I bring the tin top closer. You can quite clearly see how that is, and you can also see how the LED lights up. So there we are. That's magnetic reflection. The electromagnetic wave is reflected in a similar way, and that is why often with space diversity, due to reflections, due to changes in atmospheric conditions, a signal may be reflected onto the second outdoor antenna, And that particular antenna being on a different channel will get a better signal than maybe, say, the primary antenna. So we have a primary antenna and a secondary antenna. In the case of MIMO, multiple input, multiple output, with space diversity, the atmospheric conditions can influence the refraction and reflection of signals onto the two antennas, and that's why two antennas in a space diversity mode works extremely well. Thank you for watching. Be sure to watch my next video on modulation.